Okay, I'm going to go over the 11.2 quick check. So this has four different problems, four different gas law problems. So we're going to start off here and say, okay, well, we have a sample of nitrogen gas occupies 400 milliliters at -20. Okay, and so before I have a chance to forget, I'm going to change that -20 into Kelvin, add 273, that's going to make that 253 Kelvin. And 500 torr. What is the pressure if the sample is placed in a 1.2 liter container at 20 degrees? I'm going to change that to 293 Kelvin. Okay, so looking at my problem here, I'm going to say, well, looks like I have a P1, V1, T1, P2, V2, and T2. Okay, a sample occupies 400 milliliters, so that's 400 milliliters at 253 Kelvin and 500 torr. What is the pressure if the sample is placed in a 1.2 liter container at 293 Kelvin, and we're looking for the new pressure. Okay, now the only thing here is that I need to have both of these in the same unit, so I'm going to change this one. Say there's 1 liter for 1,000 milliliters. And so I can make 1,200 milliliters. I could have also changed my first volume to 0.4 liters, either one, just as long as they match. So now I can just substitute in. So I have P1 V1 over T1 equals P2 V2 over T2. I've changed to Kelvin, I've changed both the milliliters, we're good. So it's 500 torr times 400 milliliters divided by 253 Kelvin equals X times 1,200 milliliters all over 293 Kelvin. Now I'm going to solve for X, and you can see that this is going to be an algebra problem now. So 500 times 900 times 293 is equal to 250 times 1,200 times X, and I'll solve for X. And I get 193 torr for my answer. Okay, that is a 400 right there. It's kind of sloppy. Okay, so that's the first problem, 193 torr. Second problem, syringe contains 50 milliliters of air, has a pressure of 25 kPa. At what volume will the syringe have a pressure of 200 kPa? So it looks like here I have a volume, which is 50 milliliters, 50.0, and I have a pressure that is 25 kilopascals. And so what's my new volume? So I'm looking for my new volume when the pressure is 200 kilopascals. Okay, so I know that this is going to be, my formula is P1 times V1 is equal to P2 times V2. Now again, I have to refer back to my combined gas law, which is PV over T equals PV over T, and since the temperature is not mentioned, it means it doesn't change, so that's out of my equation. So P1 V1 equals P2 V2, substituting in, so I'm going to have 50 milliliters times 25 kilopascals is equal to X times 200, I wrote that wrong, 200 kilopascals. Now just looking at this, I can see this is going up 8 times the pressure, so this is going to go down by 8 times, okay, or I can just do the math, and so X equals 50 times 25 divided by 200. So 1/8 of 50, 6.25, and that is milliliters. Next problem. A syringe contains 50 milliliters of air and it has a pressure of 225 kilopascals and a temperature of 20. Okay, so I'm going to change that right now to 293 Kelvin. Contains how many moles? Okay, if I see moles in a problem, then I know that's going to be a PV equals nRT problem. So I'm going to find all my values. Now R is given, so it's 0.0821. That's liters, atmospheres per mole Kelvin. So I know that my pressure, which is 225 kilopascals, has to be in atmospheres. So I'm going to change that, 101.3 kilopascals for 1 atmosphere, which is going to be 2.22 atmospheres. Okay, my volume is 50 milliliters. Okay, I need to change that to liters. So I know there's 1,000 milliliters in 1 liter. So that's going to be 0.0500 liters. I'm going to move my decimal point 3 times back, so I get 0.050. Okay, how many moles? We're looking for that. And the temperature we decided is already 293 Kelvin. Okay, so we're trying to find number of moles. So, changing color, PV equals nRT. I like to adjust for N, so I'm going to say N is equal to PV over RT. And now I just substitute. So P is 2.22, V is 0.0500, okay, R is 0.0821, and my temperature 293. So I'm going to substitute those in and get my answer. I get 0.004614. And that is moles, and that's my answer. So it's a PV equals nRT problem, and I'm going to solve for N. Okay, the last problem. A 5-liter metal container with oxygen has a pressure of 3 atmospheres at 100 degrees Celsius. Again, I'm going to change that to 373 Kelvin before I forget. What mass of oxygen is in the container? Okay, so again, if I want mass, I'm probably going to have to get moles. So I know that this is a PV equals nRT problem. And we know that R is 0.0821. And again, that's liters, atmospheres per mole Kelvin. Okay, temperature we know is 373. Okay, my volume is 5 liters. So that's already in liters. I don't need to change it. My pressure is 3 atmospheres. Okay, so that's already in atmospheres. That's good. So the only thing I don't know is moles. So even though it doesn't say I need to find moles, I know that is the one thing I can find. So I'm going to go back to my equation. PV equals nRT. N equals PV over RT. I'm going to substitute in 3 times 5. That's 3.05 over R 0.0821 and 373. So that comes out to 0.4898 moles, and that's moles of oxygen. And the idea here is I can use too many significant figures because I know that's an in-between number. So I want to get the mass of oxygen. So back we just have to say moles times molecular weight. So I'm going to say 0.4898 moles of oxygen multiplied by my molar mass, so 1 mole of O2 is 32.00 grams of oxygen. And again, that was just looking at the periodic table, remembering that this is diatomic, so 16 plus 16, that's where we got the 32. And all we have to do is solve this. And my calculator says 15.674, and that's grams of oxygen. But my numbers were only two significant figures, so I'm just going to round this off to 16 grams of oxygen. And that is the last problem.